So, for our final talk, Boldy will be telling us about completeness for arbitrary finite dimensions of ZXW-calculus. Thanks very much.
Thank you. So yeah, this is joint work with Harney Wang, Razin, Leah, Richie, and Bob. And today, what I will try to explain to you is what completeness means, what the ZXW calculus is, and what qudits are. Okay, so let's get started. Luckily, we had quite a few people talking about ZX calculus today. So I'm not going to be going too much into the details of what this is. Here I just want to mention that ZX calculus, among many other things, is super useful for quantum circuit optimization, as we have just seen it, or measurement-based quantum computing, or education, and many more. But there are other frameworks too for expressing about quantum computation, such as the ZW calculus. But these two calculi both express quantum computation, but are slightly different. They have strengths in different fields. For example, the ZW is better for optical or linear optical quantum computing, or to express summation of different diagrams. And here what we did was combine these previous calculi into a single framework called the ZXW calculus. And what we saw is that this calculus is quite beneficial if we want to express Hamiltonians, for example, which results in exciting applications in quantum chemistry, or we can actually differentiate and integrate ZX diagrams using this ZX calculus, which is a ZXW calculus, which again is quite interesting in quantum machine learning. And then, so when we talk about quantum computation, what we usually mean is qubit quantum computation. That is, we have two computational basis states, 0 and 1. And with qudits, we generalize this notion to the computational basis states. So we don't just restrict ourselves to 0 and 1, but we also have 0, 1, 2, 3, and so on until d minus 1. And this is obviously beneficial because we are provided with a larger state space. Some algorithms can be simplified. It has advantages in quantum communication, and it's also beneficial for error correction. And most notably, our hardwares, most of our hardwares or many of our hardwares are native to these qudits. So our particles could be excited more and more to have high dimensional values. We just chose to use 0 and 1. And then, what is completeness? So it's quite different to what this audience might be familiar with. When it comes to graphical languages, completeness means that given two diagrams that we know equal, so they represent the same linear map, we say that a language is complete if we can prove that these two diagrams equal. So if we can show using the rules of the calculus that these two diagrams equal. So previously, completeness has been proved. I don't know if some of you may have seen it, but there has been a lot of completeness papers regarding ZX-like languages. It all started in 2014, 2014, yeah. And then it took many steps. And recently we had a nice paper proving completeness of odd prime dimensional ZX calculus, but it was only for the Clifford fragment, which is a subspace of this quantum computation, which is also easily simulable, but at the same time has nice properties. However, this work is quite general. We proved that the ZXW calculus is universally complete. This is the first universal completeness for beyond qubits. And we also showed it universal. This is a super general result. So what is the ZXW calculus? So first of all, we have these computational basis states, and we have red spiders just like in the previous talks, and they represent the computational basis states. And then we have two of our spiders, the Z spider first, which we could understand as a copying mechanism. So if you input some kind of basis state into it, it copies it, making two of the same basis state. And then we have the X spider, which corresponds to modulo addition. So if we have I and J as the inputs of this X spider, the output is going to be I modulo addition dj. And lastly, so this is the ZXW calculus. We have an extra W generator. This W generator corresponds to the standardized W state to some extent. However, if we input a 0 computational basis state, we get two zeros as the output. And if we input any J state, then we get a superposition of J0 and 0J. And this is true for all J's. So all computational basis states except for J equals 0, because that's this case. Now we have seen these Z boxes and Z spiders in the previous talks. However, we work with the more generalized version of this that we call the Z box. In the Z spider, we have an alpha parameter where alpha is a real number. And our matrices, our second diagonal element of the matrix is an exponent with this alpha. With the Z box, we generalize it to arbitrary complex phases. So obviously this is a superset of the Z spider. We could express a Z spider, but it gives us more opportunities to express more complex values. And then we are working with qudits, right? So when we have a qubit, our matrix is I 2 times 2, but with qudits we have D times D matrices. And to generalize this to qudits, we have a vector parameter with D minus 1 values, and then those values are in the diagonal of the given matrix. And then using some easy mathematical tricks, if we set a j to b1, then we can express this easily as a sum. And then this leads us to the generator Z box with any number of inputs and outputs. So this is something like a generalized Kronecker delta with a Z rotation, with a rotation around about this A vector. So then what did we prove using this ZXW calculus? We shown that the ZXW calculus is universally complete for all finite dimensions. That is, if we have any D, then we can show it that is universally complete. So any fragment, we can show that these two diagrams equal. So how did we do this? First of all, we have this thing called the map state duality in quantum computing. This means that if we can prove something with two states, then this also holds for linear maps. So we only have to consider states when proving something. And we also have a normal form in the ZXW calculus. So given any complex vector of size d to the power of m, we can construct a ZXW diagram that represents exactly that complex vector. This is done, first of all, we have the elements of this vector in the Z boxes, and then we have these things called the multipliers, and these multipliers are connected to X spiders. And the connections or the values of the multipliers are determined by the binary decomposition of the given matrix index. And then if we have a normal form, if we have a unique normal form, then completeness is kind of easy, right? So we have two diagrams, we know they equal. And then what we can do is turn both of them into this normal form. And then it's kind of obvious that then these two, then we have the rewrite steps from one to the other, because we can go from the diagram to the normal form and back from the normal form to the other diagram. So the two things equal, and we showed it. So the language is complete. But to do that, we need to show that any diagram can be turned into a normal form. And that's exactly what we do. So first we note that the structure of any state diagram can be represented as the following diagram. So we have these slices of boxes, where these boxes consist of generators. So what we do is just slice our diagram up to generators, so that we only have to care about the generators. And then first we want to turn one of these slices. So this, in A1, we only have tensor product of generators. We want to turn this into a normal form. Then we just bend this top of the diagram. This is something we can do with these graphical languages. So we grab one end and bend it. And then we need to turn A2, convert bent into a state diagram. We need to turn this into another normal form. So remember, this is again generators bent into normal forms. So that's what we need to convert now. And then this is just a tensor product of two normal forms. We turn these tensor products into a new normal form. And then what we end up with is just having to reduce these cups into a single normal form. These cups correspond to the partial trace of the normal form. So if we have that, then we can repeat this step and repeat, and then in the end, what we end up with is a single normal form, which is exactly what we need. So just to sum it up, we need to convert state generators, so generators bent into normal form, into normal forms. We have to convert tensor products into normal forms, and we have to convert partial trace normal forms into their normal form. If everything is given, then we have completeness. And this is exactly what we prove in the paper. However, it's obviously quite detailed, so I'm not going to show any details here. I just want to show you the rules of ZXW-calculus. So first of all, ZXW-calculus, we have the rules of both ZX and ZW-calculus. And then what's interesting here is that we have some new, yet unseen rules between the ZX and W algebras, which are used to prove the completeness. So first of all, rules of the qudit ZX, where we, instead of the Z spider, we have these Z boxes. One slight difference is that when we have A and B connected with any number of legs, when they fuse, they don't add up, but they multiply. And this is just because of the interpretation of the Z box, because it's not in the exponent, the parameter, but it's actually the element. We have the identity removals. We have the empty diagram. This is something unique to qudits. So if someone has only worked with qubits ZX calculus, haven't seen this, this dualizer maps computational basis state J into minus J or D minus J. And this is trivial in the qubit ZX calculus. It would be the identity, but in qudits, it's not that nice. And when we commute through a dualizer through a Z box, the phase of the Z box just flips, so the order is reversed. And then we have the usual bialgebra. Furthermore, we have the zero rule, that a Z box with the zero phase is just an X spider. We have the copy and pi commutation to say so. So these things correspond to the pi phases of the ZX calculus in qubits. We just have more of these. 2 Hadamards equal this dualizer. And also we have this multiplier that I can show you. So these multipliers are actually just connections between a Z and an X node. So in qubit quantum computing, or in qubit ZX, when you have multiple connections between Z and X, they get disconnected. However, here we work with qudits and they don't get disconnected. You can have more and more up until D connections. When you reach D, they disconnect. So that's the hop flow. So this means that the dualizer is actually just a Z and an X connected with D-1 wires. And then we can commute a KJ phase through a Z box as follows. It changes the phase of the Z box using this calculation. Then we have the rules of ZW. It's super similar to the qubit case. If we have Z boxes, they can be pushed down. If a W node is connected to 2 Z boxes that are measurements or effects, then they get added. The W node is symmetric, associative. Furthermore, we have a bialgebra between the W node and Z spiders. And lastly, the WW rule, which is quite interesting to those who are familiar with ZW calculus. So what we have in the qubit ZW calculus is that this would hold only for this. We don't need this bottom thing. However, in qudits, that would not hold anymore. And what we need, and also in qubits, you would have a fermionic swap, so it would be something slightly different. But here we could show it for this case, given that it is mapped into this subspace. And then we have the rules of ZXW. So BS0 and BSJ describe the interaction of the W node and the computational basis states. We have the KZ rule. So this KZ rule, if we think about it in qubits, it's quite obvious because these multipliers can only take the value of 1. So what we see is that this W node is connected to these Z box, the Z spiders, and the Z spider is connected with a single wire to this, and then we can apply trialgebra, and this one can be copied through, and then everything just is obvious. However, in qudits, it's quite complicated. And here I would note that this rule might be the case that could be proved using the previous rules, but it's something we failed to do so far, but it would be a super interesting direction to see how minimal this calculus could be made. And then we have the trialgebra rule, the TA, which displays a nice interaction between the 3 algebras. And this trialgebra can be generalized to have any number of Z spiders and X spiders. And given that we find a structure like this, we can always change the W nodes into X spiders and vice versa. And lastly, we have the second part of the ZXW rules. So we have this W box, which is an interesting structure. It's a Z box interacting with the W node, and then we have all the number of connections from the W down to the Z box. And this has the following interpretation. So it maps 0 to 0 and maps I, so all the other i's, into -1. and the M box is just the extension of this. And this W box can also be pushed through the W node. It interacts with a Z box by selecting the last element of the vector in the parameter and repeating it through the whole vector. We have this VA rule that is used to, if you see, we have all these boxes with A1, A2 and all these phases to a D minus 1. And then these phases could be combined using the VA rule. And then we have a single A box and then the V box. And lastly, we have the Hadamard decomposition rule, which may seem rather complicated, but actually this was a major breakthrough in our journey to prove completeness. This was the last step, and it was a very, very hard process to find this rather nice rule in the end. So using these rules, we can prove completeness. And what this completeness helped us with is we found a lot of new interesting structures in ZXW that can be used to do photonic quantum computing. So we know some applications with linear optical quantum computing, but these new structures are really useful if you want to do something nonlinear. Then it would be interesting to prove a more general completeness of the qfinite ZXW calculus that combines all these dimensions into a single framework. We have a new paper coming on speedy evaluation of ZXW diagrams, which uses a technique similar to Clifford decomposition, and it's a super interesting topic. And lastly, it would be quite interesting to analyze how we could do circuit extraction of ZXW diagrams. So circuit extraction means that we have a ZXW diagram and we want to get back a quantum circuit that we could just put on a quantum computer and run it. So how do we do that? That would be an interesting question. And that would be it. So thank you for your attention.
Thanks very much. Any questions?
Yep.
So have you thought about, so have the language be modeled in other settings than just one-dimensional Hilbert spaces? Or, so do you have other, like probably some kind of symmetric monodal categories where this language can be kind of modeled? Or is that the main focus of?
So our main focus is, so the question was if we considered other spaces in which this language would be useful, other monoidal categories, symmetric monoidal.
You're working with like linear spaces and. So you're working with like finite dimensional Hilbert spaces, and this language is modeled by that context. And you have this completeness result with respect to these finite dimensional Hilbert spaces. So I'm wondering if you have, if this language can be modeled in other categories or other monodal categories as well, or what kind of structures would you like to have?
So it, I guess, all depends on the interpretation of the diagrams and how you deal with tensor products and how you compose diagrams. I think with string diagrams you can do something similar with more general things, but we here focus on quantum computing, be it qubit or qudit.
Follow up on that. The ZX part of this theory is an example of Hopf-Frobenius algebra. And under quite broad conditions, Hopf-Frobenius algebras you can define axiomatically are always isomorphic to an example of a finite-dimensional vector space. So I think you're not going to get a lot of models of these things outside of finite-dimensional vector spaces. My question. So if I understood the talk correctly, the ZX part on ZXW for dimension t is the group algebra for ZT.
Yes.
So would anything break if you use some other group algebra there?
Such as?
Any other group T elements? Your favorite before?
I don't know this. Yeah, we can talk after the after this, maybe. Yeah.
So in this procedure of normalization, because in many coherence theorems in category theory are proved in a similar way that you kind of have this kind of let's say a word of it's a certain type, and then you use associators or whatever, and you kind of use it in a directed way, so you can get to this normal form. Let's say all the parentheses are in the right and all the identities are like destroyed. So in the similar sense, when you go to this normal form, are you able to use only one kind of rules to one direction, or do you need it? Because often the normal form is some kind of minimal element in some kind of poset structure of all possible states. So I'm wondering if it's a kind of if you can use the rules in kind of a directed way to get to the normal form. So you're giving a diagram and you go to the normal form. Are you able to kind of use only, let's say, the rules from left to right? You have these equations.
No, we can go both ways.
But when you go to the normal form,
right,
are you able to restrict yourself only to kind of using, let's say, the equation from left to right? So because, for example, in let's say the coherence theory of one of the categories, the way that MacLane proves it, he takes the associator, which like associates from the parentheses from the left to right. So he's only using the equations kind of from so taking the parentheses and moving them to the left, and using that kind of, and that's why he is able to get the normal form in this directed way. So, and this is actually important in the proof of these coherence theorems. I'm just looking for an analogy in this kind of going to the normal form.
It's more like components of a groupoid than like the bottom of a process. You're finding components in groupoid, right? But by taking a normal form, that's right.
I understood the question in terms of having a rewriting system where you've decided which direction you're going to use the rules, and then having some result which says that the result is convergent. But based on your reaction, it doesn't seem like you've thought about it in those terms, so I don't think we're going to get a satisfying answer. Are there any other questions?
Okay.
I think Matt was first.
I was just interested if you could say a bit more about what the difference is between this photonics application or what.
What do you mean differences?
Well, I mean, you said that, okay, well,
oh, how the
right for, I don't know, quantum computing, but
yeah.
Then there's, I don't know a lot about these things anyway, but it's sort of, you made it sound like this ZXW-calculus has something about it that makes it good for some things that the ZX-calculus isn't, and wasn't clear to me exactly what that was.
So when we talk about quantum computing, most of them we talk about this circuit-based quantum computation, where we have these Hadamard gates and C0, and using these gates, you can do universal quantum computing, so you can do whatever you want to do. However, there are other alternative ways to do quantum computation, and one of them, for example, uses light, and this is slightly different to this usual Hadamard and C0 things. There you have things like a beam splitter or a phase shifter, and using these things, it is also shown that you can do universal quantum computation. It's just a different structure. It has different benefits, and that's what I meant by linear optical quantum computing.
So if you want to do quantum computers Hadamard gate is not like the basic kind of.
Yes, that's right. So
It's
that's exactly correct. Yeah.
Into that particular, but they use sort of these light-based ones. They can still do the same computational things as the.
Yeah, they can do the same and also something different to what we usually do with circuit-based quantum computing. Yeah.
I think we've got time for both, so you go ahead.
So just with you had the matrix at the start of completeness results, and there was one entry, the ZX calculus is complete. What was this?
Which completeness result?
Could you go back to the slide with
At the
completeness
start
result?
at the start of your talk. Yeah. So that says that's ZX calculus is.
So yeah, this is a bit tricky. This is not ZX calculus, so this one, and this one are ZX calculus, but this is actually ZW calculus.
So now I'm wondering, like the blank entries here.
Yeah.
Like.
So this one actually proves all of these things, yeah, and all of these.
But so the other blank entries, like, are we expecting to be able to find like ZX diagrams that evaluate to the same Clifford plus T future gate, but we can't show that we can't find a rewrite?
I think we are not expecting anything anymore. Maybe with qudits, yeah.
So there's a blank square, the Clifford plus T under the.
Yeah, these things. This would be an interesting thing to look into. So I don't know if you.
Question, like, are we opinionated about the answer? Like, are we expecting it to work, or are we looking for counterexamples? Or
So what I can say right now is that so things work much nicer when it comes to prime dimensions, and that thing ZX calculus could work just as well for Clifford plus T and universal. So if you find a universal completeness of ZX, that also means the universal Clifford plus T completeness of ZX. And if someone has this result, they will skip this and no one is going to care about this anymore. Yeah.
so it's just unknown.
Yes. Yeah.
So just on this one, you said it quite nicely that when E equals 2, you've got a completeness result for the universal fragment W, and separately another one for ZX. So do you think that to get the arbitrary dimension, you actually need both X and W? Or could you imagine a proof
Right.
ZX or only Z?
So some context here. Using this result later, 3 years later, people proved the completeness of ZX by translating the generators of ZX into ZW. So what the question here is that would it be possible to do this with only ZX or ZW, not the ZXW? And the answer is for prime dimension, I suspect that we could do something like that. But with a W node, it gets super tricky. So you could construct this W node using a Toffoli gate. But constructing Toffoli gates is, as long as I'm concerned, only no in prime dimensions. So if we would have that result, that would be quite huge. I would really like to have that, but it's quite complicated so far. We tried, and it's not as easy. But for prime dimensions, I think we will be able to do that at one point.
The question is open, it's not excluded.
Yes, definitely. Yeah.
Last question, if it's quick.
It should be. I didn't see any normalization conditions on the states, like the different gates didn't necessarily conserve the norm.
We don't really care about the norms. Yeah, we do care about scalars. Scalars are preserved, but we don't care about norms.
All right, let's thank the speaker again.